And the definition of series is that it's two capacitors that are connected together end to end in such a way that the same current, they have the same current that goes, I shouldn't say the same current goes through them because the current really doesn't go through a capacitor, but I should say the same current goes through, reaches the surfaces of both capacitors, let's put it that way. The same current comes and reaches the surface of that capacitor. So you end up getting a situation where they have the same charge, Q1 equals Q2, and the same current goes through the battery, so it's equal to the total current going through the battery. Okay? And another thing is true about capacitors in series is that the negative of one capacitor is going to end up being connected to the positive of the other. Okay? So we want to know, how do capacitors in series add up? Well, what we know is their voltages add up. So the voltages add up to give you the total voltage of the source, the total voltage of the battery. Then we use the fact that V1 is equal to Q1 over C1 by definition. V2 is equal to Q2 over C2. And V total is Q total over C total. And then Q1, Q2, Q total cancel. So you end up with and then we practiced that in the lab that we did. So 1 over C1 plus 1 over C2 is equal to 1 over C total. So capacitors in series add up in such a way that the total capacitance is less than either of them. Okay, so let's say C1 was 5 microfarads, C2 was 10 microfarads. If we add them in series, we should get a number that's less than 5. 1 over 5 plus 1 over 10 is 1 over C tot. Double the top, double the denominator, we get 3 over 10. And then now invert that C tot is 10 over 3, which is 3.33. So if for any reason, let's say you had two capacitors with you, 10 and 5, but you needed a circuit with 3. So you just connect them in series. If you need a circuit with 1 microfarad, connect one more in series, one more in series. The more you connect in series, the less that it's going to be. It's going to be less than any of them, right? Okay, how about in parallel? So this is going to be parallel right here. Now this is different than next week we'll do resistors in series and parallel. So you'll see that resistors add up opposite to capacitors. So what will happen here is the current will come split into two I1, I2. So the current reaching this surface of the capacitor is different than the current reaching that surface. So this is going to be plus, 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 minus, 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 minus. The I2 will continue flowing, and then it will join with the I1, and then you will end up getting I here. So the idea is that in a parallel circuit, the currents are different, so therefore the charge is different, but the voltages are the same. The voltage drop across here is the same as the voltage drop across here. V1, V2 is equal to the V total. So to get how do the capacitors add up, you say Q total is Q1 plus Q2. So in this case, now it's the charge that adds up. The total charge of both capacitors equals to the, added up equals to the total charge of the circuit. And then Q tot is C tot V tot. Q1 is equal to C1 V1. And Q2 is C2 V2. And V tot equals V1, which equals V2. They're all the same potential difference. They all have the same potential difference across them. So V tot, V1, V2 cancel. Therefore, C tot is C1 plus C2. So if you have two capacitors that are in parallel, they enhance each other. So if you have 10 and a 5, you get 15. So if you want to make a bigger capacitor, then just keep adding them in parallel. Okay. Now, how about the energy? What's true about the energy? Both capacitors store energy, right? Is it the same energy or is it different energy? So let's talk about that a little bit. It turns out that the energy just simply adds up. The energy stored in here is not necessarily the same as this. Okay? The energy stored here plus the energy stored there is equal to the energy flowing through the battery. So energies add up. Okay? U1 plus U2 is equal to U tot. Okay? Now how could I derive that? Let's say I want to derive it. How would I derive it? Well, remember there's three formulas for the potential energy. Half Q squared over C, or half CV squared, or half QV. Which of those three forms should I use to derive this equation for the series circuit? Which of those three forms should I use? What is the same about all three of them? Their charge. So use the half Q squared over C. Right? So half Q1 squared over C1 plus half Q2 squared over C2 equals half Q total squared over C total. So if I'm trying to prove this, I have a question mark here. I don't know if it's true. I'm trying to see if it's true. So then what happens? Q1 equals Q2, which equals Q tot. Their charge of all of them is the same in series. So Q1 cancels, Q2 cancels, Q tot cancels, half cancels, half cancels, half cancels. You end up with 1 over C1 plus 1 over C2 plus equals 1 over C tot. So is that a derivation of this? Did I derive it okay? You will not see this in any textbook shown to you this way. This is very unique. Okay? So I've actually shown that capacitors add up, their energies add up using this way of proving it. And then the 1 over C1 plus 1 over C2 comes out to be the same as what we know. And then how about the parallel? Do their energies add up again? It should. Their energies should still add up. Okay? Then which form of the equation should I use? What's the same about all of them? The V, right? So half C1 V1 squared plus half C2 V2 squared equals question mark half C tot V tot squared. And then V1 cancels, V2 cancels, V tot cancels, half cancels. So C1 plus C2 equals C tot. Awesome. Nice, okay? So their energies just simply add up like a regular addition, okay? In either case.